All right. Take a pause. Look at this problem and try it on your own first. I'm gonna talk through it. Um, but the question is, how can you tell if something is an acid or a base? Now, our definition so far that we have, remember, I'm gonna do these in two different colors. We'll do let's do acid in pink and base in blue, kind of like litmus paper, right? Um, so in that case, our acid, remember, oops, is going to be a proton donor, and our base is going to be a proton acceptor. That means it's going to have a lone pair, right? That can form the bond. And our acid will have a hydrogen it can lose. So take a minute and look through these 5 different molecules and try to label which one's an acid and which one's a base. And then also try to decide which lone pair and which hydrogen in each molecule are the hydrogen that's acidic or the lone pair that's basic in the base. Okay, hopefully you've had a chance to give that a try. Let's walk through these one at a time. Now, here is the confusing part about this. A lot of these have both lone pairs and hydrogens. Not all, but most of them. And so then you're kind of stuck with this situation of like, well, but then which one is it? So we're going to talk through a few strategies for deciding that. And then later in this lecture series, we're going to talk about structural features of acids and bases in more detail. But I want to just give us something to get in the back of our minds while we start talking about acids and bases right away. So our first one that we have, I'm going to look at is right here. So we'll look right here first. So here I have a carbon bonded to 3 hydrogens, then another carbon bonded to 2 oxygens, and a hydrogen to the oxygen. So when I look at this, I see lone pairs on my oxygen atoms, and I see hydrogens that are in nonpolar bonds. So let's actually get a different color to look at this. All right, so here we go. So these are nonpolar, which means I'm going to have a pretty even distribution of electron density over that hydrogen and that carbon, right? However, this oxygen hydrogen bond right here, this one isn't going to be nonpolar. It'll be polar. There's going to be a pretty big difference, where this hydrogen is going to be pretty partially positive, and my oxygen's already going to be very partially negative. And in fact, this could perform hydrogen bonding interactions with a water molecule. Just imagine this, right? It actually has a hydrogen bond to a water molecule in solution already, right? And and we know that a covalent bond is stronger than a hydrogen bonding interaction. And that's really characterized by the distance. A hydrogen bond is much closer, and that's the stronger interaction between the two, the stronger Coulombic forces that exist between them. And then if you have more distance, it's a hydrogen bonding interaction, which is like 5% as strong as a regular bond. So, but what if one of them gets longer and the other one gets shorter, right? Then this becomes the bond, the covalent bond, and this becomes a hydrogen bond. And so you can imagine, just follow with me here, this hydrogen shifting in location, and it can form a bond very easily. And then leave the oxygen with a negative charge. It's already partially negative, and that partially negative charge is going to have a resonance structure if it exists, right? We'll be able to delocalize any negative charge over another carbon and oxygen bond that's a double bond. So these are all things that I'm noticing about the structure of this molecule that I'm not pulling from my knowledge of acids and bases. I'm pulling this strictly from when we discussed the structure of covalent molecules earlier in our general chem series. And so I'm going to need to use these structural clues to decide if I'm looking at an acid or a base intuitively. And I might not always get it right. That's why we have the ability to go and study the acidity of a molecule and just take its pH and decide. But it's important to be able to make these connections between structure and function when we look at chemistry. So that way we can be more predictive and we can really start to see the connections between how these atoms come together and how they then behave in a chemical reaction. So what I just walked through there was a lot. And we're going to walk through that level of detail later when we talk about structural features. So right now I want to kind of zoom back and look for some small patterns that we can apply again and again. So in this first one that I'm looking at, this is going to be an acid. This is actually acetic acid, household vinegar, right? And so the hydrogen here that is going to be acidic is the one that's bonded to the oxygen. And so, what I hope you see here through our first part of the conversation is that when I'm deciding if something is going to be an acid or a base, if I'm looking for an acidic hydrogen, I'm typically going to look for one that already has a partial positive charge, or one that's already hydrogen bonding to water somewhere else, or where there's already a distribution of electron density that favors that hydrogen being able to break its bond more easily. Now, all those other features I talked about help me decide which hydrogen it is, and to say this is probably an acid because what's left over after the hydrogen leaves will be stable. But looking at this, how do I know it's not a base with those lone pairs? And so when I'm looking at this, if I were, I always imagine like, well, what happens if it does accept a hydrogen? If it does, it's going to form a positive charge. It's going to form a positive charge on an oxygen, and an oxygen is really electronegative. And so that's another piece of this to remember. Like it can happen, it's just less likely for a more electronegative element to have a positive charge and more likely for an electronegative element to have a negative charge. And so, again, that's coming out of all the work we did around covalent molecules. And and so here I would say it's more likely that this is an acid. All right, let's look at our cyanide ion next, the carbon bonded to our nitrogen. So when I look at this one, I easily see a base. So here's a base. And I have two lone pairs. And I see this as a base because I don't see a hydrogen atom anywhere in the molecule. So I'm like, it can't be an acid. And so I see two lone pairs that could act as a basic lone pair, one on the nitrogen and one on the carbon. And I'm going to choose the lone pair on the carbon because it is, as we said, it's more likely for more electronegative atom to have that negative charge. And similarly, it's more likely for a less electronegative atom to be neutral. And right now, that extra electron on that carbon, it has a formal charge of -1. So because carbon isn't very electronegative, it'll be more stable if it has a formal charge of 0. All right, let's look at our next one, lithium hydroxide. So in this case, I see a hydroxide, and so that tells me right away it's a base. So anytime I see an OH minus, and this is a OH bonded to a lithium, and lithium's a metal, so this is going to be an ionic compound. And so whenever I see an OH in an ionic compound, that is always going to say base to me because that's literally the Arrhenius definition of a base. And so those ones are easier. All right, let's now go down. Let's look at NO3H2. So when I look at this molecule, similar to our first one, I see both hydrogens and I see lone pairs. But again, I see hydrogens that have a partial positive charge on them. And I see that it's overall neutral. So if it gains a proton, it's going to have a positive charge on an electronegative element. And so I'm going to see these hydrogens here that are bonded to that oxygen as likely acidic hydrogens. And this will act as an acid. right, let's look at our last one, serine. This is big, so this is kind of huge. Um, so there's a lot going on here. I see lone pairs. I also see hydrogens. And that could be acidic, that are attached to things that are going to be more electronegative than it. And honestly, like there's a lot of these partially positive hydrogens. There's one up here, one here, here, and here. And we have electronegative elements that have lone pairs. And so those would be more likely to be able to form a bond to a hydrogen. Now, I don't see anything that like it does that has a negative charge, which uh would be more stabilized by the addition of a proton because it would get to a neutral charge, which is more stable. Um, but so looking at this, the cool thing about serine is it's actually both. It's both an acid and a base. And so let me show you where it's an acid. The hydrogen that is bonded to this oxygen, which is then double bonded to another oxygen, is our most acidic hydrogen in this. Now, you can also say that hydrogen right here, this is also a little acidic too, but not as acidic as this first one that I highlighted. And so we also though have this nitrogen with a lone pair, and we've seen that before. We've seen that on ammonia, which is NH3 with a lone pair. And while nitrogen hydrogen bonds are able to hydrogen bond to a water molecule or to something else, the electronegativity difference between a nitrogen and a hydrogen is less than the difference between an oxygen and a hydrogen. So the hydrogen bonded to the oxygen is more partially positive than one that's bonded to a nitrogen. And that subtle difference that makes all the difference when it comes to acid base chemistry. And so here we actually see that this nitrogen lone pair, it acts as a base. And so what we really have with serine is we have both. And in fact, I'm going to kind of rewrite half of this. When we see, and this is an amino acid, right? So when we see amino acids in biology, we usually see that acidic hydrogen deprotonated, like removed, and we see a hydrogen added to the nitrogen side. I'm going to draw that for you really quick. And so what we see at a neutral pH, we'll talk about pH more, but when it's not acidic or basic, is that we have it acting as both an acid and a base. It's like taken the proton from within the molecule and added it to the other side, to the more basic lone pair, which I think is super cool about amino acids and really fun. So in general, I think it's important for everyone to kind of make a plan or a method or maybe a set of criteria that they look at to kind of help them guess, to get close to, is this an acid or is this a base? And getting a little bit of practice with that will make this feel a lot more intuitive, and it'll make acid base chemistry go faster. But it takes practice to kind of see these patterns. And we're going to try to show you these patterns through this lecture series and through the textbook readings. So that way you get used to seeing something that's acting as a base and something that's acting as an acid. And when in doubt, when you don't know, what you do is you look up the acidity of that compound, or the basicity, in a reference book, or you do an experiment to find out what it is. And so we'll go into more detail about structural pieces later. But in general, I think it's fair to say that acids are going to tend to have hydrogens that are bonded to something much more electronegative than it sometimes. And that bases are going to have hydroxides, or they're going to have lone pairs with negative charges, or they're going to have lone pairs with a negative formal charge on something that is less electronegative.